Okay, let's go ahead and talk about the lab that we're going to do. Actually, we're going to do this one today. Let's get this video posted this weekend. Sorry about that. But this should help you through the pre-lab and post-lab calculations if you're struggling with those. So this lab is an equilibrium lab, and it's kind of a cool lab. It's a little bit different than the ones we've done. We're actually going to use colorimetry, which someone was laughing about that last semester. I can't remember. We did calorimetry, and they said we should be doing colorimetry. Well, there we go. But basically what we're doing here is we're going to measure the concentration of something using absorbance. And this works when you have a reaction that changes color. You can actually measure the absorbance of the certain wavelengths of light. And that will basically tell you how concentrated the solution is, and there's actually a formula you can use to get you from absorbance to concentration. So that's kind of the strategy we're going to use here. And the nice thing about that is sometimes when we're working with very, 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 very low concentrations of things, it's easier to measure the concentration using this particular method. Okay. So our basic reaction here. We've got the Fe3 plus reacting with the FeSCN minus, and it's going to turn to FeSCN2 plus. And notice this is going to give us a blood red color when we do this. Okay, so when you react these things, you should get a nice color there, and we can actually observe the wavelengths that are getting absorbed and reflected. So the equilibrium constant for that expression, they give it right there. And then there's a little bit of explanation here. I think it's a little bit further down. That sort of explains what's happening here. This is going to be a little bit confusing probably as we do it. But the idea here is what we're doing first is we're starting with a series of reference solutions. And so the reference solution, so there's actually two different parts here. Really, it says part one, the reference solutions and the test solutions are prepared, and then in part two, the absorbances are measured. I think what I may have you do probably is do this. One day we're doing the reference solutions, and so that will sort of be part one, and then the next day we'll do the test solutions, because I want you to be able to, we don't have a ton of cuvettes, so I want to make sure that third and fifth hour both get to do this process today. And then, so we'll do the reference solutions today. And what that essentially does, the reference solutions, we're going to give ourselves a graph, basically, that gives us the absorbance versus the concentration. Okay, and so because the equation that relates these two things has a constant in it, and there's no real way to know what that constant is unless we figure it out experimentally. So basically what we're going to do here is we are going to, the reference solutions, we're going to use Le Chatelier. Okay, so we're going to make a huge excess of the Fe3 plus. We're going to add way more of that along with the FeSCN minus ions. Okay, and so what that's going to do is we can assume that the FeSCN minus ions all completely convert into this, because it's big time the limiting reactant here. Okay, and so what we're essentially doing with this, go back up to the, let's see here, back up to the equation. Okay, so what we're doing is we are adding a ton of this, which pushes the equilibrium pretty much all the way over here, so that pretty much all of this gets converted into this. That's a lot of arrows just then, but what that means is if we know the initial concentration of the FeSCN minus that we're starting with, then that's essentially going to tell us the FeSCN2 plus concentration. And that's going to be helpful because then we can measure that concentration versus the absorbance, and that'll help us, because as you can see here, Beer's law is this equation right here. A is the absorption of light. That's what we're going to actually be measuring. E is the absorptivity of the sample, and B is the cell path. Okay, and then C is the concentration. So we can relate the absorbency to the concentration, but it's through this formula where we don't know the E and the B. And so what we basically have to do here is make a graph. Okay, so what we're going to do essentially, after we prepare our reference solutions, we're going to use our reference solutions, and I can't remember which one is being graphed on which side, but absorbance versus concentration, essentially. And we're going to have a line that kind of goes like this, okay? And so instead of using Beer's law, because we don't know the E and the B, then once we have our standard line here, our best fit line, then let's say that we measure an absorbance of one of our unknowns to be right here. We can just trace it over here and figure out what our concentration is, okay? And so that's kind of the strategy here, to figure this out experimentally without knowing the E and the B. Okay, so pre-lab questions, define equilibrium. I hope you guys can do that at this point. The reaction for the formation of diamine silver ion is as follows. That's a complex ion, by the way, that's being formed here. It says write the equilibrium constant expression for the reaction. Again, I don't think I need to write that up there because I think you guys can do this. Although, I guess for the next part, if we're going to go through this together, we probably need to go over this. So the K is going to be equal to the concentration of the product, AgNH3 2 plus over Ag plus times NH3 squared. Okay, so that's our equilibrium constant expression. Now it says the experiment was carried out to determine the value of the equilibrium constant for the reaction. All right, so basically what we're doing here, and they're not doing a great job of explaining this, but we've got three things that we need to calculate here in this particular question. Calculate the equilibrium concentration of Ag plus, the equilibrium concentration of NH3, and the value of the equilibrium constant. I'm trying to think if I have room to do this here or not. I'm going to maybe just write over what's here. See if that's legible. All right, so what we have to start with here is we have a total moles of Ag plus present and total moles of NH3 present. Okay, so essentially these are our, we can turn these into starting concentrations for the Ag plus and the NH3. And then we also know the concentration in the Ag NH3 2 plus at equilibrium. Okay, and we know the total solution volume is 100 milliliters. So, knowing all that information, we should be able to figure out our equilibrium constant, and I guess our equilibrium concentrations as well. So, best thing to do for this is probably just to set up an ice table. Let me see. I'll erase this and we'll go. Just a little bit here. Is that plenty of room for this? Okay, so if I'm making an ice table, it'd be easiest to just use the equation they already have. Okay, so there's my ice table. My initial concentration of my Ag plus here. I know the total moles of Ag plus that are present, 3.6 times 10 to the negative third. Okay, and I know the volume of the solution is 100 milliliters. So if I want to know the concentration, I just take 3.6 times 10 to the negative third divided by 0.1. And so my concentration here is 0.036. Okay, and then my concentration in the NH3, again, 6.9 times 10 to the negative third divided by 0.1. Moles divided by liters. That's going to be 0.069. Okay, and then we can assume that we don't have any of this to start with, or concentration, I guess I should write, is 0. Okay. So then the one thing that we know is our equilibrium concentration here is 3.4 times 10 to the negative second. Alright, so that means that this must have changed by plus 3.4 times 10 to the negative second. Now remember, the change column here, or the change row, is when we can use the stoichiometry for. And so if that changes by 3.4 times 10 to the negative second, because of the 2 in front of the NH3, that's going to change by twice as much, but it's in the negative direction. This is, there should be an arrow there, so double arrow. So it's going to be a change in the negative direction. In other words, the concentration is going to go down. So if I multiply the 3.4 times 10 to the negative second times 2, then it's actually going to go down by 0.068, which is very close to all of it. And then the 0.036, actually, if I want to rewrite that, the 3.4 times 10 to the negative second, it is just 0.034. Okay, so what I end up with here is 0.002 and 0.001 for my ending concentrations here, which again can be expressed as 2 times 10 to the negative third for the Ag plus, and 1 times 10 to the negative third for the NH3. And then once I know that, now that I've written my equilibrium expression, you can calculate the equilibrium constant. I think you guys can probably figure that part out. You're just plugging into the equilibrium expressions with all three of your equilibrium concentrations. Okay. After we've done that, number 3 here, the equilibrium concentration of the FeSCN2 plus ions in each reference solution listed below is essentially equal to the concentration of the SCN minus ions in solution before any reaction occurs. Use the Chatelier's principle to explain why this statement is true. Well, we kind of talked about that one earlier when I was explaining how the lab is going to work. So I think hopefully that makes sense. Just, see what I said before when I was referencing the equation, the equilibrium equation that we're going to use in this one. I think you can answer that question. All right, number 4, the 5 reference solutions in part 1 are prepared by mixing 0.2 molar FeNO33 solution and 0.00020 KSCN solution in the amounts listed in the following table. Well, one thing to notice here, okay, again, is that this is way more concentrated than this, okay, which is, again, that's going to be our strategy when we're making the reference solutions. Okay, so this is going to help us with some of the Postlab calculations we have to do here. The concentration of Fe3 plus ions in the first reference solution before any reaction occurs can be calculated using the dilution equation. Okay, and that's essentially going to help you find the final concentration after the solution is diluted. It says use the dilution equation to calculate the concentration of Sc minus ions in the 5 reference solutions before any reaction occurs. Alright, so just one thing to remember here, you got KSCN solution. As soon as you put that into, this is an ionic compound, so as soon as you put that into a solution, it's actually going to split apart into K plus and SCN minus, and the concentration is going to be equal because this is a 1-to-1 ratio here in this formula. So if we have 0.00020 molar KSCN, then we also have 0.00020 molar SCN minus. Okay, so we know our initial concentration of the SCN minus, but what they're saying here is we're adding that to the FeNO33 solution. So we're starting out with a 2 milliliter solution. We're going to end up with a 10.0 milliliter solution. So what you have to do is an M1V1 equals M2V2, where you've got your initial molarity is 0.00020, multiply that by your initial volume, which is 2 milliliters, and that's going to be equal to your M2 times 10 milliliters, because once we add the iron to it, that just dilutes the solution. Okay, so then that will give you your concentration of the SCN minus in the reference solutions. Okay, so you have to make sure that you do that. You have to take into account that this thing is going to be diluted before it even reacts, which makes it even less concentrated. Okay, and then the following table summarizes the volumes of Fe3 plus and SCN minus stock solutions. Will be mixed together to prepare the test solutions in part 1. Use the dilution equation to calculate the concentration of Fe3 plus and SCN minus ions in each of the test solutions before any reaction occurs. Enter these results in the calculations in the scientific notation in data table 2. And the final volume of each test solution again is 10. So the nice thing about this pre-lab is it actually sort of helps you out with the actual lab. So number 4 here, they're telling you to where is it? we're going to enter these values in data table 1 as the FeSCN2+. Okay, so again, let me emphasize here that the FeSCN2+ concentration is going to be equal to the SCN minus concentration, the initial SCN minus concentration, because we're assuming that we have so much of the iron nitrate that's going to push the equilibrium all the way to the right, and all of this SCN minus ends up getting converted into FeSCN2+. Okay, that's why we're putting it into the data table as FeSCN2+. Okay, so let me just kind of show you the data table. You're going to put number 4 in. Skip it right now. There we go. Okay, so number 4 on the Prelab, you're going to put right here where it says FeSCN2+, data table 1 for the reference solutions. Okay, then on number 5 in the Prelab, it's too far. Number 5 in the Prelab, it says put in scientific notation in data table 2. Okay, the results of these calculations. So we're gonna calculate the concentrations of the Fe3+ and the SCN minus ions. Okay, and then we're gonna put those into the data table. All right. So when you find the Fe3+ concentrations and the SCN minus concentrations, then that's gonna go right here. Okay, and they actually have these starred to show. See the pre-lab questions for calculations. Okay, so that shows you basically exactly where to put those. All right. So once you have done that, then you've done the lab and you've gotten all of your absorbance data, which your absorbance data you're going to be putting right here, and you're also going to be putting it in data table 1. Okay. So that's where you're going to be measuring the absorbance of your reference solutions and your test solutions. And that's all, really all the data you're going to be collecting in class is just measuring those absorbances. Okay, I will tell you how to do the colorimetry measurements. We've actually got a computer program that's going to help us do that, and hopefully we'll get good data here. Now, data table 3, these are the results, and I believe that the Postlab kind of helps you out with how to get all the calculations you need for data table 3. Okay, so what you're going to do once you have all your data, you are going to graph the concentration. See, I picked the wrong axes here. It's concentration on the x-axis and the absorbance on the y-axis. All right. And so what you're going to do here is you're going to do a graph using your reference concentrations. Okay. And so then in the test solutions, and this is what I was saying before, you can figure out once you have your graph made. Now the graph, again, this is just for the reference solutions. I'm trying to look and see where it says that. Graph paper, molar concentration of FeSCN2+. The best fitting straight line to the data points. It doesn't really say, but that's what you're doing. Okay, so this graph right here, this is going to come from your reference solutions, because we know the concentration of our FeSCN2+ in our reference solutions because we have so much of the iron nitrate, iron 3 nitrate, I guess, that we're going to push the equilibrium all the way to the right, and all of the SCN minus equals the FeSCN2+. Okay, and so we will have that FeSCN2+ concentration. And I guess this graph, maybe I should make this clear. This graph is going to come straight from this data table right here. Okay, so this is the data table you're going to want to look at to make that graph. Okay. Then once you have done that, now you have a nice little reference graph that you can use to figure this out. Okay, That's going to tell you your concentration based on your absorbance in your test solutions, the ones that we don't know, 6 through 10, okay? And so then you're going to be able to get those concentrations there. And then comes kind of the tricky part. And the tricky part basically is then that it's really not even that tricky, but you got this equation. Okay, Fe3 plus and FeSCN minus are combining to make the FeSCN2 plus. And we can write an equilibrium expression for that particular equation, okay? And so once you write your equilibrium expression for that, which is going to be KQ equals FeSCN2 plus over, well, I'll tell you what, you can write this equilibrium expression. What I really need to show you here is that we're going to make another ice table, okay? So essentially what we have here, we have the starting concentration of, we have the ending concentration at FeSCN2 plus. And we can assume that the starting concentration is 0, okay? That's going to give us all the changes. So, and actually we do have the starting concentration at Fe3 plus and the FeSCN minus also, okay? Let me show you where you have those, just so you know exactly where you're looking for all this stuff, because that can get a little bit confusing here. So back up here, we have the initial concentration at the very beginning of the Fe3 plus and the FeSCN minus, okay? So once we have that, we can come back down here, okay? And then what we have figured out using the graph is the FeSCN2 plus, okay? Then we can use that use that in the ice table to figure out the concentration of Fe3 plus and the FeSCN minus at equilibrium, okay? Because we know the starting concentration of the FeSCN2 plus is 0, okay? And so then we know that the change, and I guess I need to map this out a little bit better. I'm hoping that this makes sense. I'm not doing a great job of explaining it right now. Okay, so if we've got our ice table, what we're going to know this, the Fe3 plus concentration. We're going to know the FeSCN minus concentration at the beginning, and we're going to know that the FeSCN2 plus is 0, okay? Then we're also going to know, based on the graph, we're going to know what the FeSCN2 plus concentration is at equilibrium, okay? That's going to give us this change, okay, and that's going to be a positive change. And then this is just a one-to-one-to-one stoichiometry here, so whatever that change is, this is going to be negative that, okay, and that should give us then our equilibrium concentrations. Right. Once we have all three of these, you just plug them into your equilibrium expression, and that's going to give you your equilibrium constant. Okay. Now we're going to have to do this 5 times. Okay, you're going to have to do this calculation 5 times, which I know is kind of a pain, but that'll get you 5 equilibrium constants, and then you're going to calculate the average value. And then you can figure out the average deviation, which I think it tells you how to do that at the bottom here. Okay, so that's basically the game plan for this lab. Hopefully that makes sense. Let me see what they actually have written on the Postlab calculations and analysis. I think they're probably saying everything that I just said. The unknown concentration of the FeSCN2 plus ions in the test solutions can be determined from the graph. Okay, find the absorbance value of the test solution, read across to the best fit straight line curve, and then down to the x-axis to find the concentration. All right, so that, again, we're just using the graph that we made from the reference solutions to figure that out. 3, record the FeSCN2 plus concentration for each solution. Okay, we talked about that. 4, calculate the equilibrium concentration of the Fe3 plus ions in each test solution. And they're going about that a little bit differently. Honestly, again, I would just use an ice table because that's what we've been practicing in class. So I think that's probably the best way to do number 4 and number 5. Okay? And then number 6 here, it says use equation 4 in the background section to calculate the value of the equilibrium constant, which We talked about that as well. Number 7, calculate the mean or the average value of the equilibrium constant, and then calculate the average deviation for KEQ. And what they say to find that, find the absolute value, the difference between each individual value of the equilibrium constant and the mean, and then take the average of those differences. Okay, so what you're going to do for that is you're basically going to come back, oops, too far. You're going to come back here, okay, and you're going to look at your average value, okay, and you're going to compare number 1 to the average, and you're going to see the difference between those two, and then you're going to compare number 2 to the average, and number 3 to the average, and then you're going to take the differences of those, and you're going to take the average of them, okay, and that's the number that's going to go in this average deviation here. Okay, now let's see what else we've got on here. Oops. The average deviation describes the precision of the results. Does the precision indicate the equilibrium constant is indeed a constant? Okay, so I'm going to let you kind of think about that one based on your data. Number 10, describe the possible sources of error in this experiment. Again, that's something that you can think about. Hopefully, at this point, figure out some of the things that would have could have made that error greater. Postlab questions: explain what is meant by an equilibrium constant. Was the value constant for all your experiments? Should it be? Okay, you can answer that question. What does the calculated value of the equilibrium constant indicate regarding the degree of completeness of the reaction? In other words, at equilibrium, are there mostly products, reactants, or relatively large amounts of both? Okay, so again, we've talked about this in class, and this is just a good review right here. But the size of the equilibrium constant tells you something. If it's a very small number, it means that the equilibrium favors the reactants, which means there's going to be more of the reactants. If it's a large number, there's going to be mostly products. Explain what a spectrophotometer is and what it measures. Describe how standard solutions were obtained and used to determine concentrations of unknown. Okay, hopefully after everything else we've talked about, that makes sense to you. Spectrophotometer basically measures absorbances, and I guess maybe I can talk a little bit more about that quickly. Basically what a spectrophotometer does is it measures the absorbance of certain wavelengths of light. Okay, so if you have a colored solution, that colored solution is absorbing certain wavelengths of light and it's reflecting others. The ones that we see are the ones that are being reflected back to us. Okay, so what you want to do is you want to basically pick, so if we've got something that's blood red, then we probably want to pick something more on the blue end of the spectrum, because what that's going to do is the reason we see red in the colors in the solutions here is because that's the color that's being reflected back to us. So that's not the color that's being absorbed. The color that's being absorbed is most likely other colors in the spectrum, especially like the blue side of the spectrum. So we're going to measure the absorbance at wavelengths that are in the blue spectrum of light. Okay, because then, and actually I think I'm kind of answering number 4 as I go through this. What that's going to do is that's going to tell us the absorbance, how much of that light it's absorbing, and we can use that, sort of relate it to our concentration. The higher the concentration, the more blood red it is, and therefore the more blue it's absorbing, the more red it's reflecting. Okay. When you use a spectrophotometer, should you set the wavelength of light to be the same color as the solution, or would a different color be more appropriate? We just talked about that. The color you see is being reflected back to you, not being absorbed, so it would be hard to measure the absorbance using the wavelength of light that. Sorry, I lost my train of thought. Let me start that over. It would be hard to measure the absorbance based on the light that's being reflected back to you. Okay. Color of light chosen for this experiment. You can look at what, and I want you to just actually look this up. I'm going to tell this to you. The color of light chosen for this experiment, we're at 450 nanometers is the wavelength of light we're looking at, so I will let you look up what color of light that actually is, but I think you might already be able to figure it out based on what we talked about. And the color of the FeSCN2 plus complex ion obviously is blood red. 5, what degree of precision can you obtain with the spectrophotometer that was used? What is the major source of error in the experiment? I kind of led you in that question. Just think about how concentrated our solutions were, and think how precise we can be with our measurements. Okay, and that might actually be a useful discussion of significant figures and how they can sometimes limit the precision you can have in the lab. And then suggest other experiments in which a spectrophotometer would be useful. I'll let you try and figure that one out. Any other times when measuring the absorbance of something might be a useful thing. Okay? All right, I think that's pretty much it. Still a lot of calculations to do, but this is not nearly as bulky as the last Postlab, so hopefully you'll enjoy this one a little bit more. All right, we'll see you in class.